Okay, Marvin,
You again. What now, Sam?
tell me a programmer joke.
Why do programmers prefer dark mode? Because light attracts bugs.
That right there is a 400 rupee or $4 microcontroller talking back to me. And it's running a full AI chatbot pipeline. Let's get into it. If you have been following this channel, you probably noticed a pattern. We first explored the ICS43434 MEMS microphone, datasheet, schematics, and code. Then came OpenAI Whisper speech recognition. Then TinyML voice command detection running directly on ESP32. Later, Max 98357 audio amplifier came into picture. So this playlist was never about copy pasting firmware. It was about building the foundations required to actually put pieces together on how voice systems work. Namaste and welcome back to Avinashee Tech. Most AI chatbot projects you will find online, well, they use same plug and play firmware, copy pasted code, and a tiny display cramped with LLM text. But think about it. Does Alexa have a screen full of text? Does Google Assistant? No. I mean, yeah, few recent versions have started rolling out displays, but still,
Alexa,
it's
start.
unnecessary for majority of cases. In case of online chatbot projects, you get a low resolution tiny text that was not needed for a eyes-free application anyway. But the bigger thing missing in most projects is proper wake word detection. Devices like Alexa are always listening, but only for one specific keyword. Hi Alexa, OK Google. Only after detecting that wake word does the actual internet communication begin. That improves privacy, reduces bandwidth, and saves processing power. So I wanted to implement the same architecture on ESP32. I selected the wake word Marvin because it's already present inside Google's speech commands dataset that we used earlier for TinyML training. The ICS43434 microphone continuously listens for the word Marvin. Once detected, ESP32 pauses wake word detection and plays a response through the Max 98357 amplifier. You heard it in the start and will hear it soon again. For this pre-recorded audio, I have used 11 Labs TTS platform. A free account on 11 Labs gives enough credits for such small audio clips. Okay, after that a short beep tells us recording has started. That's our cue to ask anything. Few seconds of audio is recorded and sent via HTTPS to a speech-to-text API. Text then comes back as a response. Initially, I wanted to use OpenAI API directly for speech-to-text, but after facing some billing issues while making requests, your poor engineer switched to Groq. Talking about Groq, it offers a free plan along with paid options as well. What Groq basically provides is AI inference infrastructure using their own custom hardware called LPUs. Not GPUs, not TPUs, but LPUs. The interesting part is that Groq itself usually does not create these AI models, but instead companies like OpenAI, Meta, Alibaba, and others provide the model weights. Groq optimizes these and deploys them on their own LPU hardware, and users access those models through Groq's API endpoints. Now, there is a great article on their official website explaining LPUs and how they help reduce latency, but honestly, even I am still learning many of those technical details and buzzwords myself. Now, if we navigate to the developer section, we get the option to create an API key. One important thing, make sure to save that API key somewhere safe when you create it, because later you won't be able to retrieve it again. Think of it like those Mission Impossible recordings that self-destruct after playing once. Inside the dashboard, you can also monitor useful information like number of requests, audio duration, logs, timestamps, model used, HTTP status codes, and so on. Currently, for speech-to-text, Groq supports OpenAI Whisper models, including Whisper Large and Whisper Large Turbo. Now, we have already explored Whisper in one of our previous videos, but the earlier workflow was very different. At that time, ESP32 simply streamed microphone audio to the PC over UART. Python saved that audio as a WAV file, and transcription happened on the computer itself. This time, the PC is completely out of the picture. ESP32 directly sends the recorded audio to the internet using an HTTPS request. For speech to text, two modes are available, transcription and translation. In our case, we are using transcription. Now for free users, Groq currently allows audio uploads up to 25 MB. While our recording is just a tiny 3-second mono wave file, at 16 kHz sample rate, 16-bit audio, single channel mono, the size comes close to around 96 kilobytes. I intentionally kept the recording window small to reduce memory usage, reduce latency, and keep things manageable for this tiny microcontroller. And honestly, most short voice queries fit comfortably within that 3-second window anyway. Maybe in future I will try pushing that limit further. One thing I completely underestimated during this project was how brutal HTTPS requests can become from a microcontroller side. Seriously, miss a single carriage return or a line feed, and suddenly you are staring at HTTP errors wondering what exactly broke. So, before banging your head debugging ESP32 firmware, it is always better to first verify the API using a simple curl request. Let's quickly do that. Inside the command prompt, we will start with a basic request. First, the transcription URL. Then, the API secret key, which I obviously won't show here. Before the key, we need a bearer keyword. Then comes our wave audio file. And finally, the model, which I will select as Whisper Large Turbo. Hit enter, and yes, the request works successfully. So now we know the API key is correct, endpoint is correct, and request format is valid. Only after this point does it make sense to go ahead with the firmware, and there are also many additional parameters available in the request body like language selection, temperature, and more. But for a simple test, this minimal request is enough. Alright, enough theory, let's finally see this thing in action. I have my ESP32 dev board here, connected with ICS43434 mic and MAX 98357 amplifier. Both of this chip make use of I2S communication. The setup is a bit messy with jumper cables, but spare me for that. After booting, ESP32 sits quietly in the background, continuously listening for the wake word. Okay, Marvin.
You again. What now, Sham?
And right after the wake word is detected, TinyML inference pauses, a short beep plays, and recording for speech to text begins. Who is President of India? Another beep, recording finished. And once the HTTPS request is completed, we can see the transcription response arriving back as text from the API. At multiple points during development, I honestly wasn't even sure if ESP32 could reliably pull this off. Application code memory became a serious limitation very quickly, and that is exactly why many voice assistant projects online make use of ESP32 S3 boards. More flash, more RAM, faster PSRAM, no worry about code size or buffer length. But hang on, we have still discussed only half of the project, because till now ESP32 can hear, record, and transcribe. In the next video, we will connect this pipeline to an actual language model, generate responses, then convert that response text back into speech. So if you are into embedded systems, TinyML, IoT, or things like that, or you just enjoy building things instead of copy pasting, consider subscribing to the channel and supporting us. This is Avinashee Tech, signing off.